All right, so today we're going to be talking about gas stoichiometry, and it doesn't really differ a whole lot from regular stoichiometry. Anytime you can get moles, you can do stoichiometry, right? So the first step is get moles. Get number of moles. Somehow, right? So either use the ideal gas law, right? So either use PV equals nRT, or maybe I give you the mass in grams, and then you would convert grams to moles. Those are the two most common ways to get number of moles. Of course, if we're talking about the gas phase, this is obviously more likely than this because gases are not solids, right? And then step 2 of any stoichiometric problem is multiply by the mole ratio. What does that come from? Where do you get that mole ratio? From the balanced chemical equation. And then you would convert final number as problem asks. So whatever the problem asks you to do, you do it, right? So in the gas phase, for instance, you could use PV equals nRT for substance number 1, multiply the mole ratio, get number of moles of substance number 2, and then maybe plug that back into PV equals nRT to get the volume of that gas, for instance. So gas stoichiometry, just like solution stoichiometry, it kind of varies, right? Because if based on what you're given, you figure out how you get number of moles. This is always step 2. And then you're going to convert, again, based on the problem. Now, there is one thing I want to talk about before we get into the nuts and bolts of doing stoichiometry, and that is the scenario that occurs when you collect a gas over water. Collecting gas over water. So in the lab, this is something that you do experimentally. Let's pretend you're doing an experiment and you're trying to capture a gas. Well, there are a lot of problems that could come up, right? Because when you capture a gas, it's easy to just get out and you don't have it anymore, right? So one of the ways that you capture gases is you do it in water. So let's pretend you've got some sort of reaction taking place. We've got it in some sort of sealed container here. And we don't care what this reaction is. It's producing a gas. So we use our tubing, and then we've got a second container here also sealed. And so our gas is being produced here. It's going to go through the tubing into the water and then bubble up. And so this is the gas that we're interested in. Right? That's one of the ways that you can actually design an experiment to capture a gas and know that you're being relatively accurate. But here's a problem. If this gas is being collected over water, is it just the gas that we're interested in, or is there something else in this space? Wouldn't there also be water molecules in here too? Yes, because the water is going to be vaporizing as well. So there's also water in here. Okay, so that's the problem we deal with. And this is not a challenge that's difficult to overcome. You would just need to know the total pressure. Because think about what we learned last time. P total would be equal to the pressure of the gas that we want plus the pressure of the water vapor. Right? So if we need, say, the pressure of that gas to do our PV equals nRT calculation, if we know the total atmospheric pressure, you can look that up, and you happen to know the water vapor, how would you get the pressure of the gas? You just subtract that out, right? So let's pretend that on that given day, the total atmospheric pressure is, I don't know, 1.03 is equal to pressure of the gas, and then you determine that the water vapor's pressure is 0.41, right? Could you get the pressure of the gas? You just subtract this from this, right? I want to show you one like this because I'm pretty sure on the homework, on the gases homework, there's a question involving a gas being collected over water. So if you know the total atmospheric pressure and you know the pressure of the water vapor, to get the pressure of the gas you're interested in, you just subtract it out. Easy enough. And then you can take this and plug it into PV equals nRT and you're off to the races. Okay? So don't let it throw you off. I can't remember for certain if there is, but just in case, if there is one on your homework about collecting gases over water, it's not difficult to deal with. Do we see how to address this situation? Yes. All right, so now let's do some stoichiometry. So let's pretend that we're doing a reaction, gas phase. Let's do the Haber process. This is actually an equilibrium reaction, but we won't worry about that right now. We'll deal with equilibrium next semester. Is this balanced?
No.
What do we need in order to make this balanced?
Triple H2 and then double H3.
There we go. Okay, so obviously before we do any stoichiometry, we have to balance the equation. Why? What would happen if we forgot to balance this equation? Step 2 would be a mess. All right, so let's just pretend that these are the data that we're given. I'm just going to list it underneath, which is what I would recommend doing anyway, right? I could write out this big, long word problem and spend 10 minutes writing it out, or we could just list it underneath, which is what I would recommend. So let's pretend that the pressure here is 0.74 atmospheres. Let's pretend the volume is 8.0 liters. And let's pretend the temperature is 23 degrees Celsius. And here, the pressure is 0.65 atmospheres, and the volume is 7.5 liters, and the temperature is 25 degrees Celsius. And I want to know what, let's just say for fun, what is the volume if the pressure here is 1.01 atmospheres and the temperature is 27 degrees Celsius. Could we do this problem? Is this something we could do? Let's devise a plan. We know information about two reactants, so off the top, what does that guarantee we're going to have to do? Limiting reagent, right? We got to do it twice because we have to figure out which one we're going to run out of first. So step 1 of stoichiometry is always get number of moles. Do we have a way of getting number of moles here? Yes. How do we get number of moles? If PV is equal to nRT, then N is just what? PV over RT. Do we have everything we need to do that? We've got PV, R is constant, and there's T. PV, R is constant, there's T. So we would get number of moles of H2 using PV equals nRT, right? We get number of moles of N2 using PV equals nRT. Then we do our stoichiometry, and that would give us number of moles of NH3. And it's asking for volume. Do we have everything we need in order to do a volume calculation? If PV is equal to nRT, then V would be nRT over P. Do we have all those things? And we would solve for R is constant, T is given, and P is given. So could we do this problem? Do we have everything we need? Yes. Does everybody understand what we're doing? See the big picture. I like to show you the big picture before we go through the arithmetic, because if you don't understand where we're going, the arithmetic's kind of pointless. We ready to do the math? Ready to do the math? All right, so I'm going to erase my little game plan here. Let's first calculate number of moles of each one of these so we can add it to our list. So number of moles of H2, PV equals nRT, so N is equal to PV over RT. So P, 0.74, V, 8 liters, R is a constant, and then what's that temperature in Kelvin? All right, so atmospheres cancels, liters cancels, Kelvin cancel. 1 over moles gives me moles. So let's do some arithmetic. 0.74 times 8 divided by 0.08206 times 296. I got 0.244. Let's just carry out extra digits. We're going to round at the end. Do we agree? Those of you doing it along with me, do we agree? All right. So let me erase this. Add our value here. Now let's calculate number of moles of N2. N is equal to PV over RT. So 0.65 atmospheres. Volume is 7.5 liters. 0.08206 liter atmospheres per mole Kelvin. And what's this one? 290. What do we add it to? 273 plus 25 is 298. Try to make sure that you're paying attention a little bit, right? So 0.65 times 7.5 divided by 0.08206 times 298. I get 0.199. 199 moles. Do we agree, those of you following along with me, to get the same number? Okay. So now we've got number of moles. Now here's the nice thing about the stoichiometry of it. When we're doing regular stoichiometry, quote unquote, you got to do grams to moles, mole ratio, then moles back to grams, right? Would we need to do grams to moles? No, it's already in moles, right? We don't have grams. So would we waste our time with converting this to grams for any reason? No, that would be pointless, because then we have to convert it back to moles. And then when we get our final answer here, do we need to convert it to grams? We need to find number of grams of NH3? Would that be a useful use of our time? No. Why would we not want this in grams? Because can I plug grams into PV equals nRT? No. So the step 2 of stoichiometry is pretty easy, right? But we just have to do it twice, because we have to figure out who's the limiting reagent. So for H2, 0.244 moles H2 times, for every 3 moles of H2 that I use, I produce 2 moles of ammonia. And then let's do it for N2 and then compare. 0.199 for every 1 mole that I use, I make 2 moles of ammonia. So moles cancels. So I multiply straight across and divide up. So times 2. Carry out some extra digits, we'll round at the end. 0.399 moles. And then here, 0.244 times 2 divided by 3 gives me 0.163 moles. So which one's the limiting reagent? Hydrogen's the limiting reagent, right? Because it produces the smaller number of moles of the product that I'm interested in. So which value do I keep? 0.163 or 0.399? The 0.163, right? So N is equal to 0.163 moles. Does everybody understand how we did step 2, the stoichiometry step, the mole ratio step? And now the problem asks, what's the volume of that? Do I have everything I need in order to calculate volume? Yeah, just plug that back into PV equals nRT. So PV is equal to nRT. So V would just be nRT over P. Or you could just plug it straight in and then do the arithmetic like you learned in algebra class. It's not going to be any different. I just like to rearrange it first and then plug in because I can put my units in, and that'll help me make sure I didn't make a silly arrangement error. So 0.163 moles, 0.1163 moles. R is a constant, meter atmospheres per mole, Kelvin, and then temperature. What would this be in Kelvin? 300 divided by my pressure, which is 1.01 atmospheres. All right, so mole cancel, Kelvin cancel, atmospheres cancel. I'm left with units of liters, which is what I want. So I set it up correctly. So that times 0.08206 times 300 divided by 1.01. And I'm keeping 2 sig figs. So 3.96, which would round to 4.0. And my unit would be liters. How do we feel about that? How do we feel about this?
Simple, basic.
All right, you ready to try something along these lines? Yes? All right, I'm going to give you the equation. I'm going to give you some data, and then you take it away. Let's do forming water vapor. And then here are the data. Let's pretend that this is I want to know what's the pressure inside this flask. The volume is all right. There are your data. There's the equation. I'll pause the recording and give you time to try that. Okay, before we can begin, there's something we need to check. Is this a balanced equation?
No,
What do I need in order to have it balanced?
a 2 on hydrogen and a 2 on H2O.
That's right. So if we miss this detail, right, that's going to cause problems for us later on because we have to have a balanced chemical equation for step 2 of stoichiometry. So what do we need to do first? We need to get number of moles. And is this just a one-time number of moles, or do we have to do it twice?
Twice.
Got to do it twice, right? Because I know information about both of my substances. What if I didn't know this? Then my life would be a lot easier, right? Because I only have to do it once. But I'm not that lucky. I have to know both information. All right, so let's calculate number of moles of H2 and number of moles of O2. So PV over RT. So 0.54 atmospheres times 5 liters over 0.08206 liter atmospheres per mole Kelvin. And then what's my Kelvin temperature here?
289.
289 Kelvin. Okay, so atmospheres, liters, Kelvin. Let's go ahead and set the other one up. Number of moles of O2 is also PV over RT. So 0.73 times the volume, 3.5. 0.08206 liter atmospheres per mole Kelvin. And then what's my Kelvin temperature here?
292.
Okay, so Everything I want to go away goes away in terms of my units, which is good. 0.54 times 5 divided by 0.08206 times 289. I got 0.114 and 0.73 times 3.5 divided by 0.08206 times 292. I got 0.107. Do we agree on those two numbers?
Yes.
All right, so let's move that information over here. N equals. Okay, so now what am I going to do? What's my second step? We need to do a mole ratio. So let's do it for H2. 0.114 moles H2 for every 2 that I use. I make 2 of water vapor. So my number doesn't change, just my units, right? So 0.114 moles H2O. And then for O2, take my numbers, 0.107 moles O2 for every 1 mole that I use. And make 2 moles of water. I can't tell you the number of students who just out of habit go ahead and convert this to grams, right? But is that necessary?
No.
No, because you can't plug grams into ideal gas law. All right, so 107.107 times 2 gives me 0.214 moles H2O. So who's the limiting reagent?
Hydrogen.
Hydrogen would be the limiting reagent, which makes oxygen gas the excess reagent. So which one of these do I use?
Hydrogen.
Use this value. So N is equal to 0.114 moles. All right, now what am I doing? Yes, Matt. What formula do I use?
P equals.
All right, the ideal gas law. PV is equal to nRT. We're solving for P, right? So P would be nRT over V. So 0.114 moles times 0.08206 liter atmospheres per mole Kelvin. And what's my temperature?
It's 293.
293 Kelvin over my volume, which is 7.5 liters. Liters, Kelvin, moles. Gives me units of atmospheres, which is what I want. So 0.114 times 0.08206 times 293 divided by 7.5. Rounding to 2 sig figs. So I get 0.365, which rounding to 2 sig figs would be 0.37. Oops, not moles. Atmospheres. Do we agree? We agree. How do we feel about doing gas stoichiometry kinds of problems? Not too bad, are they? Okay. I'm going to give you another kind of problem. See if you can do this one. All right, let's just, actually we can keep that same reaction. Let's see, the camera, you're going out of focus on me again. All right, so let's see. We've got, this is a problem that I wrote in advance, so I don't have to make up numbers off the top of my head. 1.3 liters. And it is at a temperature of 21.5 degrees Celsius. And this is collected over water. And let's see, the vapor pressure, I guess this would be a bad one to collect over water, wouldn't it? So let's make a different reaction. We'll still use O2 though. Oh, that would be a bad one to do over water vapor too, because it would produce water. Let's just go back to Haber process. Well, vapor pressure of the water is 15 torr. And the total atmospheric pressure is 49 torr. And I want to know how many moles of NH3 do I have? All right, so I'll pause the recording, give you a chance to try that one. Okay, before we can do any stoichiometry, we have to balance the equation. What are the coefficients?
3 on the H2 and 2 on NH3.
Right. Gotta make sure our equation's balanced. Okay, so this is being collected over water. So how do I get the pressure here?
P total equals pressure of your gas plus your vapor pressure of water.
Right, so it would be taking the total atmospheric pressure is 49, right? And subtracting from that 15. Does everyone see why we're doing that? So what do you get when you get the pressure in torr? What's the pressure in torr?
34 torr.
34 torr. And it wants to know how many moles are present here. So we get a little bit of a break here because we don't have to do limiting reactants. We don't have to plug back into the ideal gas law. This one's a nice, easy one. But there is a problem. Can I keep that in torr?
No.
No. How do I convert torr to atmospheres?
Divided by 760.
Right, they are 760 torr per atmosphere. So when you get that in atmospheres, 734 divided by 760 gives me 0.0447 atmospheres. And then we've got a problem with our temperature. What is our temperature in Kelvin?
2.
What?
294.
294.5 Kelvin. Do we have to do anything with the liters, or is that okay?
That's okay.
That's okay. So what do I need to do from all this mess?
Solve for your number of moles of N2.
Right, we need to get number of moles. So PV is equal to nRT. So N is equal to PV over RT. So my pressure is 0.0447 atmospheres. My temperature is 294.5. That's the volume. Plug it in the volume. Oops. The volume is 1.3. R is constant. Temperature is 294.5. Atmospheres and liters, Kelvin. So times 1.3 divided by 0.8206 times 294.5 gives me a very low number of moles. But look how low my pressure is. I mean, that's to be expected. Okay, do we agree on number of moles?
Yes.
Now what do I do?
You have molar ratio into NH3.
Right, so now what we need to do is do the mole ratio step, and then I'm done. because the problem doesn't ask me to put it back into PV equals nRT in any way. It's just saying how many moles are there. So that one's really straightforward. N2, there's 1 mole of N2 consumed for every 2 moles ammonia that I produce. So times 2. And I get 2 sig figs this time. So 0.0048 moles. Do we agree?
Yep.
All right, there's one more little unit I want to teach you quickly, just in case it's on the homework. It's called mole fraction. It's very easy calculation, very, very, very easy calculation. We don't use molarity when we're talking about gases, right? Because there's no solute, there's no solvent. But if we have a mixture of gases and you want to express that ratio, you can use the mole fraction. So mole fraction, we represent it with the Greek letter chi. And there are 2 ways you can calculate it. So it could be N over N total, or you can do it by pressures, P over P total. Okay? So it's a very easy calculation. You can do it using gas pressure, or you can do it based on number of moles. It's pretty straightforward. So I'm going to give you one to try. Just make sure we know what we're doing. Let's see. If the mole fraction is 0.781 and the total pressure is 2.35 atmospheres, what is the partial pressure of neon? So we've got neon here we're looking at. If the mole fraction is 0.781 and the total pressure is 2.35 atmospheres, what's the partial pressure of neon? I'll pause it and let you think about that one. All right, let's go over this one. So this one we're using number of moles or pressures? We're using pressures, right? So we're using option 1. So let's just plug everything in. 0.781. By the way, this would end up being unitless because these would all cancel out, right? So that's why it's got no units. Is equal to P of the neon over the total pressure, which is 2.35. So what is the pressure of the neon? You just multiply by 2.35. So 0.781 times 2.35 gives me, keeping 3 sig figs, 1.84. And my unit would be what? Whatever the unit of total pressure is. Do we agree? Questions on that? All right, last one I'm going to give you, a stoichiometry problem, because we can't end on something not easy.
It's a Friday.
Yes, got to make up for the fact that I will be seeing you on Monday, though, right?
Ooh, we should be sent home with homework, I think. More homework.
Well, you've got homework online.
True.
Okay, so let's just get ourselves a theoretical experiment going on here. We've got X, Y, solid, decomposing into X gas and Y gas. They're both monatomic. All right, so you've got a sample. Let's use the experiment here. You've got a sample of the solid in here. Here's the solid. And there's a Bunsen burner. So there's our Bunsen burner. You don't have to sketch this. I'm just trying to sketch it for you so that you can have an idea of what you're doing. There's a gas. It's decomposing, and it's going into water and bubbling up. All right, so we're doing a collection over water type experiment. Hey, it actually went into focus when I moved away. Okay, so let's just give you some data here. We've got 14 liters, and it's at 30.5 degrees Celsius. And because this is over water, the pressure of the water is 165 millimeters mercury, and the atmospheric pressure is 878. And the molar mass of this is 173 grams per mole. And I want to know, what is the mass of the XY sample? So, try that one out. All right, let's go over this one. So, we're going to obviously need to get number of moles, right? Number of moles is what we'll need to get. Do we have enough information to get number of moles here? No, that doesn't make any sense, right? So what do we need? We need to get number of moles here somehow. How can we do that? We can use the ideal gas law, so now we just need to check all our units, make sure they're all in sync with what they need to be. 14 liters, is that okay?
Yeah.
Celsius, is that okay?
No.
What is that in Kelvin?
303.5.
What about pressure?
That's way off.
Now this is being collected above water, right? So we've got water vapor in there, and we've got the gas X, whatever this monatomic gas is, right? So how do we get the pressure of gas X? Right, so the pressure of this gas, unknown X, is just 878 minus 165. So what'd you get there?
713.
713 millimeters mercury. Is millimeters mercury an okay unit for ideal gas law? No. What's the conversion factor? 760 millimeters mercury. Millimeters Hg. For 1 atmosphere. So that comes out to be 713 divided by 760 gives me, I'll keep some extra decimal places, 9382 atmospheres. Okay, now what am I going to do? Do I have everything I need to get number of moles now? Yes. So N of X, number of moles of X, is just PV over RT, right? Because PV is equal to nRT. So the pressure is 0.9382 atmospheres times the volume of 14 liters divided by constant 0.08206 liter atmospheres per mole Kelvin times the temperature, which is 303.5. So all that goes away. So I get times 14 divided by 0.08206 times 303.5. I get 0.5274 moles. Do we agree? Okay, now what do I need to do?
Take that mole ratio.
You do stoichiometry, the mole ratio step, right? So that's X. And the mole ratio is 1 to 1, but I still would like to see this step so that I know that you know how to go from this unit to this unit, right? So for every 1 mole of X that I make, I used 1 mole of X. Y, so the number doesn't change, just my units. So that's 0.5274 moles of X. Y. And now I'm in the home stretch. How do I get the mass? I know moles. I gave you the molar mass, Right, so 0.5274 moles of XY times 173 grams per mole. So times 173. And then I'm keeping 2 sig figs. So my calculator spits out 91.23, blah, blah, blah. So that's just 91 grams. Do we agree?
Yes.
Any questions on how we do gas stoichiometry? Pretty easy, right? All right, so that's where we'll end. Have a great 3-day weekend.